multi-electron atom. That means the atom which has the more than one electrons has attraction force with the nucleus. But in addition, that electron-electron repulsion also is there. That means every electron has the repulsion with other electrons in the atom. So the stability of an electron in this multi-electron atoms is because the total attractive interaction, it is more than the repulsive interactions. Attractive interactions is between the electron and nucleus, which is more than the repulsion interaction within the electrons. So in general, the repulsive interactions of the electrons in the outer shells and with the electrons in the inner shell are more important. That means that repulsive interactions which happen in between the outer shell's electrons with the inner shell electrons, that we'll consider now. The attractive interactions of electrons increases with the increase of the positive charge on the nucleus. We know it. Positive charge of the nucleus we generally symbolized by the ZE, capital Z, small letter E. But due to the presence of the electrons in the inner shells, the electrons in the outer shells will not experience the attraction due to this positive charge ZE. It will always feel less attraction due to the electrons presence in the inner shells. This effect will be lowered. That means the attraction between the nucleus and outer shell electrons, this is lowered due to the partial spreading of positive charge on the nucleus by the inner shell electrons. That means due to the presence of the inner electrons, the full charge of the nucleus ZE, it will not fill with the outer shell electrons for attraction. And this effect is known as the shielding effect or shielding of the outer shell electrons from the nucleus by the inner shell electrons. And in that case, now what will be the net positive charge? Because now net positive charge is less than ZE. And we can symbolize this, the effective nuclear charge, as Z effective E. Capital Z subscript in small letter EFF and multiplied by the E. So this shielding of the outer electrons from the nucleus by the inner shell electrons, then the attractive force experienced by the outer shell electrons increases with increase the nuclear charge. Because if nuclear charge ZE will increase, in addition then Z effective E also will increase, though the shielding comes from the inner shell electrons for the outer electrons. So both the attractive and repulsive interactions depend on the shell and shape of the orbital in which the electron is present. For example, what is the example? That electrons present in spherical shape, that means s orbital. S orbital is spherical shaped. We already discussed in our previous class. And this electron present in the s orbital, it shields the outer electrons from the nucleus more effectively than the electrons present in p orbitals. That means the electrons present in the s orbital, it has more shielding power than the electrons present in p orbitals. Similarly, the electrons present in p orbitals shield the outer electrons from the nucleus more than the electrons present in d orbitals. That means the electrons in s orbitals, it has the most shielding power, and then it is comparatively less shielding powers for the electrons present in p orbitals, and then it is further less the shielding power of the electrons present in the d orbitals. And within a shell, that means when the principal number is same, shell represents by the principal quantum number n. We know from the previous class. So within a shell, due to the spherical shape of s orbitals, the s orbital electrons spend more time close to the nucleus in comparison to the p orbital electron, we spend more time in the vicinity of the nucleus in comparison to the d electrons. In s orbitals, in a particular shell, it is very close to the nucleus, and in comparison to the p orbitals, and again so now what we can generalize is that for a given shell, that means in the same principal quantum number, the effective nuclear charge experienced by the electron decreases with increasing of azimuthal quantum number, because we know that p orbital azimuthal quantum number 1, and for d orbital azimuthal quantum number is 2. So with increasing of the azimuthal quantum number, the Z effective, that means the effective nuclear charge will be decreases with the increase of this azimuthal quantum number L value. That means the s orbital electrons, we know for s orbitals L is equal to 0, the least, and in this case it will be more tightly bound to the nucleus. That means Z effective nuclear charge is more for the electrons in s orbitals, and then it will further decrease for the electrons in p orbitals, and which will be further decrease for the electrons in d orbitals. Energy of electrons in s orbitals will be lower, that is more negative, because we know that the s orbitals is in ground state. If we consider some multi-electron systems, and in this case the energy of the electrons in this s orbital, it will be lower than that of the p orbitals electrons, and which again, that means the orbitals in p orbital, it has also less energy than the electrons in the d orbitals, and so on. Since the extent of shielding from the nucleus is different for electrons in different orbitals, it leads to the splitting of energy levels within the same cell. Because due to the shielding effect, from our understanding now, that in the same shell, the energy level is different. That means splitting of energy levels is happening. And so the energy of electrons in an orbital depends upon the values of n and l. Because n is the principal quantum number. It also one parameter for the counting of the energy, and azimuthal quantum L, that also accountable for the energy of electrons in this particular shell. So due to the variation of the n and L, in that respect, energy level we can count. So mathematically, it is very complicated things, but in general, one simple rule is there, that the lower the value of n plus L, that means the summation of azimuthal quantum number and principal quantum number, if it is lower for an orbital, then the lower is its energy. And if two orbitals have the same value of n plus L, in that case, what will happen? In that case, the principal quantum number n, for which orbital is lower, it will have the lower energy. So this is the simple rule. And on this basis, some problem also you'll find in your exam, and you can easily solve it. Now we'll see the arrangement of the orbitals with increasing energy on the basis of the n plus n rule, what just now I described. So if you go the lower size, then energy will increase. So for the 1s, what is the value of principal quantum number n? Yes, 1. And s, what is the azimuthal quantum number? For s, it is 0. So ultimately, n plus L, it is equal to 1 plus 0 is equal to 1. So it is the lowest value. So 1s has lowest energy. And then the energy will increase for the 2s. How? Again, for the n plus L rules. For 2s, 2 means it is the principal quantum number, that is value of n. And s, we know for the s always the azimuthal quantum number L is equal to 0. So if you add these two values, then ultimately it will come the result 2. That means n plus L is equal to 2. So it is, this 2 is more than the 1. So 1s is less energy, and comparatively for 2s it is the more energy. And further, if you go for 2p orbitals, this 2, it is the value of n, and p, we know from the understanding from our previous class that for p, the azimuthal quantum number is 1. And so if you add this, then for the value of n plus L is equal to 2 plus 1 is equal to 3. So again, it has the more energy compared to the 2s orbitals. And in this way, if you go down, then energy will increase because the n plus L value will be increased. You can see in this table. Here, one case is there, that rule is there where the n plus L is equal for orbitals. In that case, if the principal quantum number n is lower, and then its energy of that with that quantum numbers will have the less energy. So in this case, in this table, you can see the 3D. For 3D, principal quantum number is 3, and for D, we know the azimuthal quantum number is 2. And in this case, n plus L is 3 plus 2 is 5. And now if you consider the 4p, the n value is 4, and that p, its L value is 1. So these also n plus L is 4 plus 1 is 5. So these two particular case, the n plus L, for both cases it is the 5, but for the 3D, the principal quantum number is 3. So definitely, as per the rule, the 3D has less energy than 4p.